Homework 8 is all about mutual inductance, except we do have a couple problems, the last two, that are about last one and the second to last one is about capacitors and charging at different times. Like there's two switches that flip. And then the second one is another one with two switches with an inductor. But most of these are mutual inductance, and we're going to consider each case. The first one right here, 7.68, we got the current going into this dot and out of this dot. And what we're going to do is we're going to find IOT, VOT, blah, blah, blah. And to do that, well, IOT is going to be I1T plus I2T. We're going to need that later. I might as well actually write out the rest. So equations for components, I'll get to that in a moment actually. But we're going to keep that KCL in mind. Now, since the inductors are in parallel with each other, we can use the parallel inductor equivalency, but there's a little bit of a wrinkle. This mutual inductance has to be accounted for. And the way we'll do that, say LEQ is going to be L1, we'll say is 5 Henry, times L2, which is 10 Henry, and minus the mutual inductance, which is five squared, divided by L1 plus L2. And this is the part that's a little bit confusing. Whenever you have opposite dots, you're going to have it add at the bottom right here. It'll be 2 times whatever M is. So simplifying this expression, we're going to get 1 Henry is the equivalent inductance. We can redraw the circuit. Actually, redraw the circuit. This will be for time greater than 0, because the switch is closed. And I'll say that's 80 volts. This is 20 ohms. And this is 1 Henry. Alright. Now, excuse that being a little lopsided, but you get what I'm doing. Alright, so I'll do my equations. Actually, let me move this over a little bit. Hold on. I want to make sure that all of this gets relatively clean, so I'll just redraw it. Okay. I'll go ahead and label it too. So VO is still going to be the voltage drop across the equivalent inductor, and nothing has changed there. And IO of T is still the current going through the resistor. 20 ohm, 1 Henry, 80 volts. Okay. So I'm going to call this ground. It's going to make this VOT and this 80 volts. We'll go ahead and do equations. $80 minus VOT divided by 20 is IOT, and VOT equals the inductance, so this is 1 Henry, times the derivative with respect to time of IOT. So, first thing I want to do before I move on is I want to get the initial conditions for the circuit. Now, there's no current moving through either of these inductors at time equals 0. Or sorry, time equals 0 minus, right before the switch is closed. And as we know, the current in an inductor cannot change instantaneously, because it would require infinite energy, which we don't have. So the initial current is 0 amps. And we can find the final current real quickly. If this becomes a short, as say VOT tends to 0, when the inductor at the steady state basically has a very small parasitic resistance, at least usually compared to the resistance it was in a circuit. In this case, like a practical circuit, maybe the inductor would make a difference, but not here. This is ideal inductor. So VOT, or not VOT, IL infinity is going to be 80 volts divided by the 20 ohms, which is 4 amps. And we'll keep that in mind as we move forward. We can find out what VO0 plus is. Now this is different from VO0 minus, because VO0 minus is 0, but after the switch is thrown, it's not anymore. And since the current right here is still 0, because it can't change instantaneously, that means that the voltage drop across the resistor is 0, and that VO0 plus is 80 volts. So we can think about also VO infinity. Like I said before, the inductor is going to become kind of like a short after it reaches the steady state. So we can just say that the voltage drop across the inductor is 0 volts at infinity. So we're going to use those later on to solve our differential equation. So we already have an expression for IoT. We're going to substitute that in here and say that VOT equals D 80 minus VOT divided by 20, bracket that, dt. Now I'm going to pull the 1/20 out, and this derivative is going to go to 0, it's a constant. So we're left with VOT equals negative 1/20 d VOT dt. Going to move it to the other side so we can get in our standard form. dVOT dt. Going to divide, or once we're adding it to the other side, it's going to become plus. And we're going to divide by 1/20, which incidentally is tau. And you can think about it also because L equivalent over R equivalent, that's 1/20. Because the ideal voltage source has 0 internal resistance, so equivalent resistance is 20. Anyway, that means that our solution to the differential equation for the voltage is going to be VOT is 0 plus A80 minus 0 times e to the minus t over tau, and tau is 9/20, so it's going to become 20t, and the unit is volts. Okay, so from this, we can go ahead and plug in VOT into IoT and get the expression for IoT. We can also do it by solving the differential equation using the initial and final current, but I'm going to do it this way. So 80 minus 80 e to the minus 20t divided by 20 equals 4 minus 4 e to the minus 20t amperes. Now, the problem also asks one thing: does your answers make sense in terms of known circuit behavior? Well, if you look at these expressions right here, this is going to decay to 0 at infinity, and at 1, it's going to be 80. Same deal here. It's going to start at 0 and increase to 4. So these answers, they make physical sense. And we can go ahead and move on to finding the I1T and I2T. Now to do that, we're going to have to do something a little bit tricky. We're going to go back to our equation for mutual inductance. And I believe I picked L1 to be the 5 Henry inductor. So I'm just going to write the expression out. di1 dt minus, in this case, the mutual inductance, because they're both are the opposite side dots. That's why it's minus. So if we plug in 80 e to the minus 20t for VOT, L1 is 5 di1 dt minus 5 di2 dt. Okay. So the tricky part is going to be that we got a derivative going on here. Now, if you remember our KCL, IO is I1 plus I2. Take the derivative of all that business, DIO dt blah 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 equals di1 dt, etc. So we can use that to make a substitution. Now, incidentally, DIO dt, it happens to be the same as the voltage expression. That's just a coincidence in this problem. So we can, if we go ahead and substitute it in and we solve for di2 dt, we're going to get, 80 e to the minus 20t minus di1 t dt. That's going to be, we're going to substitute that in to here and solve. Ultimately, we're going to get an expression like this. 80 e to the minus 20t equals 5 di1 dt minus 5 times 80 e to the minus 20t minus di1 dt. Simplify this out, we're going to get, see, 400, so it's going to work out to, let's see, 480 divided by 10. Yeah. So this is going to end up being that di1 t dt equals 48 e to the minus 20t. And if we integrate from 0 to t, this is just a separable differential equation. We're going to move this dt over there and integrate both sides. So integrate the, I'll just go ahead and write it in here. I1t is going to equal the integral with respect to time. I don't even have to do that. I'll just do the solution because it's exponential. You guys know this one. E to the minus 20t from 0 to t. That means that I1t is going to end up being 2.4 minus 2.4 e to the minus 20 t amperes. Now, we could do this whole thing again to find I2t, but using Kirchhoff's circuit law, or sorry, current law, we can just do 4 minus 2.4, and you get 1.6 e to the minus 20 t amperes. Yeah, and these answers make sense. Well, does it make sense for these values? Yes, it does. We still get 4 amps in, 4 amps out. Still get, we start with 0 amps, we end up with 4. We start with 80 volts, we go down to 0. So all these answers make sense with non-circuit behavior, and we've solved it correctly. 7.69 is a lot like the last problem, except for one tiny little difference. Instead of one current going into the dot and the other one leaving, both of these dots are having a current going into them. Now the same thing still applies. There's no energy in the circuit, so these currents are going to be 0. Which means that since EEL0 minus, well, I'll get to that in a moment. Let me go ahead, I'll do my KCL. Just so that way we're all on the same page here. I don't want to get ahead of myself. Okay. Now, we've got 2 inductors in parallel again, so we can use our parallel inductance equation with one minor change. So L equivalent is going to be L1, which is 2 times L2, which is 18. We're still going to have minus the 4m, or sorry, minus m squared, which is 4 in this case. We're still going to have 2 plus 18, but instead of being plus 2m, like it is up here, instead of being plus 2m, we're going to do minus 2m. So go ahead and do 2 times 4. Okay. So this ends up being, that's 8, 20. So 20 divided by 12, which I believe is 5/3. So 1.67-ish. Let's say 1.67 Henry. All right. So I'm going to consider the equivalent circuit once again. We're going to analyze that equivalent circuit. Makes the math really simple. That's the value. And we're going to have 50/3 ohm. And this is 100 volts. Okay. So I'll write out my equations. IoT let me just put these in just to make clear that I'm talking about those same voltages and currents. Nothing has changed other than I made an equivalency. So IoT is going to be man, I'm getting really forgetful. Sorry about that. 100 minus VOT divided by the resistance. I'll keep it as 50/3 for now. It may be a little bit confusing. Usually to keep it, switch, change it, flip it, or whatever it is when you divide by a reciprocal or divide by a fraction. But I'll keep it like that for now, and you'll see why. So VOT is going to be the inductance, so 1.67 times DIOT dt. Okay. So we're going to plug in everything. Well, let me actually find the initial and final conditions, because we're going to need those. So IO 0 minus is going to be IO 0 plus, for the reason we discussed before. And the voltage VO 0 plus, since the current is 0 and the voltage drop across the resistor is 0, that's going to be 100 volts. And VO infinity once you reach a steady state, is going to be 0 volts. So just keep those in mind. Oh, yeah, we'll also do IO infinity. This is going to be, let's see, 100 divided by, so 300 divided by 56 amperes. Okay. And we're going to use those to check our work at the very end. So I'll go ahead and wall this off so we don't mix up the math. I'm going to substitute in this whole expression for IO. This is going to become VOT is 1.67 Henry, and derivative of 100 minus VOT divided by 50 over 3 dt. And just like before, derivative of a constant is always 0. I'm going to pull the 50 over 3 out. VOT is going to be 1.67 times 50 over 3. And it's going to be minus, so dVOT dt. Just using derivative rules to make it simpler. The linearity property, I believe. Anyway, so let me find out what 1.67 times 50 is. Oh, sorry. I made a little bit of a mistake. I'm multiplying by 3 and dividing by 50. 1.67 times 3 divided by 50 is 1/10. Okay. So tau is going to be 1/10 dVOT dt plus VOT divided by tau equals 0. So the solution to our differential equation, we're going to keep VO0 is 100 and VO infinity is 0. So VOT is going to be 100 e to the minus t over tau, which is 10 volts. All right, so now we can get IoT the same way we did before. We're going to plug it in VOT into our original expression. So IoT is going to be 100 minus 100 e to the minus 10t divided by 50 over 3. So that's going to be 300 minus 300 e to the minus 10t divided by 50. Am I right? Let's see. 300 divided by 50. Yeah, okay. So that means IoT is going to be 6 minus 6 e to the minus 10t amperes. Okay. So now we're going to find I1t and I2t. And we're going to use that same process we did in the last problem, where we use the expression for mutual inductance, dI1 dt. But instead, like it shows up here, instead of it being a minus, it's going to be plus. That's very important. It's going to be m and then di2 dt. So I'm going to kind of skip ahead just a little bit. dRO dt equals di1 dt plus di2 dt. just like before, we're just going to take the derivative of I0 plus I1 plus I2, the KCL we did earlier. Now don't worry about me not putting the t's there. They're still time varying. I just don't want to write it out all over again. So end up simplifying all of this. We plug in di. We take the derivative of I0 with respect to time. We're going to get 60. Yeah, because it's derivative constant is 0. And minus 6 times minus 10 and minus 10t. So yeah, it's going to be 60. So we can say that di2 t dt equals 60, not 6, 60 e to the minus 10t minus di1 t dt. So we're gonna substitute that in to here. And we're gonna solve. So if VOT is 100 e to the minus 10t volts, and we have L1 is 2 Henry, di1 t dt, and it's plus m. M is 4, I think. Yeah, it's 4 Henry. So plus 4, we're going to put in I2, so it's going to be 60 e to the minus 10t minus di1 t dt. If we simplify this out, so it's going to be 240, and I'm going to subtract from both sides, so it's going to be minus 240, minus 240, that's going to be 2 minus 4 equals minus 2. So minus 240, or not 240, sorry. 240, or 100 minus 140 is minus 140, or 240. Okay, let me think. 100 minus 240 minus 140. Okay. So I'm going to divide by the negative 2, and that'll make put this in. E to the minus 10t equals di1 t dt, which means that I1t equals the integral from 0 to t of 70 e to the minus 10t dt, which is minus 7. I'll just put this here, minus 7 over 10, which is minus 7, e to the minus 10t from 0 to t. We plug in the 0 and the t. I'll pull the minus out. So minus 7 e to the minus 10t minus minus e to the 0, which is 1. That means we get 7 minus 7 e to the minus 10t amperes. And that is I1t. So this might be a little bit confusing because we're like 7 amps, but our maximum current for I/O has to be 6 amps. And you're right. The reason why the I2 current is going to end up being negative is because they're basically the inductors, their fields are interfering in such a way that this one is pushing, the other one is not. Anyway, so that means that if we use KCL, I2t has to be the negative of that. So it'll be minus 1 e to the minus 10t amperes. So that's consistent with the known circuit behavior. And we've solved everything correctly. So let's move on to the next one, which I believe is the same problem, but we flip the dots. All right, so I was misremembering the one with the dots flipping ends up being the ones right below this one, the next problem. I think I mentioned that before. Anyway, it's not important. So we've got no energy stored in the circuit at time equals before the switch is closed. So the current flowing through these inductors is going to be 0 amps. You can say IL 0 equals IL, or IL 0 minus equals IL 0 plus. So that's going to be 0 amps. And IL infinity is going to be Ohm's law, 80 over 40 equals 2 amps. Okay, so that's our boundaries for what the current can possibly be based on the physics of the circuit. Anyway, so we've got a bit of a complication here. These two inductors makes the math a little bit more complicated. So what we're going to do is we're going to do an equivalent inductance. And since these are in series, it's not going to be that fraction like we saw before. It'll be something like this. L1 plus L2. And this is going to be plus 2, or sorry, not plus. They don't add in this case. Minus 2m. So that means that if L1 is 5 plus 10 minus 2.5 times 5, or not 5, times 2, that's going to be 10 Henry as our equivalent inductance. So if we already have IL0 and IL infinity, we can go ahead and find IoT right away. Well, it's not IoT, it's just IT. Hold on. IT right away. Let me just write this in here. So IT is going to be I infinity plus I0 minus I infinity e to the minus, not 10, minus t over tau. So we can calculate tau because we already have the equivalent inductance. It's going to be L over R. So 10 Henry over 40 ohm is 1/4. So I can get the expression for IT, and we're going to use this to find V1 and V2T. Oops. So let's go ahead and skip the drama. IT is going to be 2 plus 0 minus 2, so minus 2 e to the minus t over tau, which is 4t amperes. So that's consistent with what we were expecting. And now we're going to be able to find V1 and V2t using that current. So V1t is going to be our first inductance, so L1 di1, not di1, di dt, and it's going to be minus m di dt. There's only one current in the circuit, so that means V1t is 5 Henry minus the initial inductance, which is 2.5. I'm going to factor out the di from both sides. We'll just take the derivative of I of t, so derivative of 2 minus e to the minus 4t dt. Yeah, that's fine. I'll update you later. Sorry about that. So we're going to take the derivative of all this business. That's going to become 0. Get rid of this, so minus 2 times minus 4 e to the minus 4t, so that's going to be 8. Okay. So I end up with 2.5 times 8 is 20? Yeah, it's 20. So V1t is going to end up being 20 e to the minus 4t volts. We can use that same logic, or we can just do a KVL, 80 minus 20 to 60. So that's going to be our expected answer. We're going to do it the math way to be rigorous. So L2 is, let's see, we got 10 Henry minus 2.5, which is the mutual inductance, derivative with respect to time of e to the minus 4t dt. It's going to be the same derivative, so it's going to be 8 e minus 2 times 7.5, which is going to be 60 e to the minus 4t volts. So yeah, these answers make sense. The voltages add up to 80, so it's physically possible. Currents are within the limits of what's possible, so these answers make sense in terms of non-circuit behavior. We're going to look at this same circuit again, but we're going to look at it with the dots flipped. That's going to be the next problem. Okay, so I did a little bit of creative artistry with the last problem, so we can make this more clear. Let me actually go ahead and put this here. Okay. So if the currents go entering the both of the dots, whenever we add up or do our LE equivalent, then the inductors are working together instead of working against each other. So we're going to have the 5 plus the 10 plus the 2.5 times 2. That's going to become 20 Henry. Go ahead and draw the little circuit. $20 Henry and 40 ohms. This is still 80 volts. All right, so our IL0 minus equals IL0 plus, not let's do I0 minus is going to equal I0 plus. Still going to be 0 amps because the current can't change instantaneously. And IO infinity is going to be Ohm's law, 2 amps. Just like before. So basically the only thing that changes here is our time constant and the way that the voltage is split between the two inductors, which we'll see in a moment. So we know tau is going to be L over R, or L equivalent over R. So 20 over 40 is 1/2. So 500 milliseconds. That means IT is going to be I infinity, which is 2, plus the initial current, which is 0, minus 2, which is e to the minus 2t amperes. And to find V1T. We're going to do, let's see, L1 I'll say is 5. Oh, that's not a question, it is 5. And unlike the last case where we were adding them up, we were going, or yeah, where we were subtracting, I should say. We're going to add up. So we're going to have 5 plus 2.5 Henry as the mutual inductance plus L1 and times the derivative of the current with respect to time, 2t dt. So that's going to be 7.5 times minus 2 times minus 2 is 4. So 30 e to the minus 2t volts. That's going to be V1t. Now V2t is going to be 10 plus 2.5, so L2 plus the mutual inductance, derivative, blah, blah, blah. We already know it's going to be 4 e to the minus 2t. So this is going to end up being 50 e to the minus 2t volts. So I hope I didn't go too fast or cut out too many steps, but I think at this point we've done the whole business with the I infinity, I zero enough times that you guys kind of understand what's going on. So let's move on to the next problem. Okay, so for 7.76, we're going to come back to capacitors just for a moment. Now, don't be intimidated by the double switches. And 2 switches just means that we have to analyze 2 different circuits, basically. And it turns out that the circuit will not be able to reach the steady state in 10 microseconds. And we'll see why in a minute. But switch 1 closes at time equals 0, switch 2 closes at time equals 10 microseconds. We're going to find VOT for time greater than 0. First thing I want to do, though, is I want to find out the initial and final behavior for this whole circuit. The initial one, we can find the final one pretty easily if we set this whole bit at the bottom of the ground. We're going to keep that as ground throughout the whole process and say that this would be the voltage VO initially, I guess. That may be misleading, so I'm just going to keep it like this. Just say this is a voltage here, this is a VOT, and this is 30 volts. So to find the final voltage, we're basically going to find out what the voltage drop across this resistor is. And if you, well, maybe actually do the initial voltage first. So VO0 minus, it's going to be VO0 plus because the voltage across the capacitor cannot change instantaneously. That'll become important in a moment. And since there's no energy stored in the circuit, 0 volts. Now, V0 infinity for, if we pretend that this switch doesn't exist and we just analyze all this business, is going to be the voltage drop across the resistor, but flipped. So we have current going in this way, and this is 0. That means that this has to be negative for it to be, well, I just wrote the answer there, but it's pretty simple. Anyway, for current to be going this way, this has to be a negative voltage, which ends up being negative 20. And this is more positive than this, basically. So anyway, we're going to do Ohm's law, 5 milliamps times 4 kilo ohms is minus 20 volts. So that would be if the capacitor was allowed to charge all the way up from that first half of the circuit. So we're going to go ahead and analyze that first half first. Say this is time equals 0 to time equals 10 microseconds. Just this interval, I guess, would be a good way to think about it. So we're going to have a current source, 5 milliamps, and 4 kilo ohm resistor. And we're going to have our capacitor. This is 20 nanofarad. This is going to become VOT, because we're keeping the same ground reference. Okay, now for the currents. Now I'm going to choose the current directions, because the capacitor current is quite arbitrary, really. I can put it either way I want. It's not like Ohm's law. Well, it is like Ohm's law. If I put if I say put it the other way, say it was going up, and instead of being VC, it would be 0 minus VOT. But since I want it to go down, I'm going to have the VCT minus 0. That's just going to make the answer, the math cleaner. So don't worry about my current direction too much. If you follow the equations right, it will come out in the wash, so to speak. So I1T is going to be over here. I hope it's not too scribbly. KCL, we have 5 milliamps going in. ICT going in. And I1 leaving. And you'll see why I did that in a moment. Equations for components. 0 minus VOT, so negative VOT divided by 4K is I1T. And ICT will be, like I said before, it will firstly write in the capacitance. It'll be the derivative with respect to time of the voltage drop across the capacitor, which is VOT minus 0 dt. So now we're going to go ahead and solve. Now, we can't do, since there's the current source in the circuit, we can't do we can't just say this is ICT, because it's not. I1T is ICT plus 5 milliamps. So if we substitute that in, let's do 5 milliamps plus ICT, so 20 E minus 9 DVOT dt equals negative VOT over 4K. So now I'm going to multiply both sides by 4K, and that's going to end up being 20 plus, I'm going to write, let's see, that's 20 times that is 80 to the minus 6, and dVOT dt equals minus VOT. So we're going to get into the standard form. Let me actually do, let me find out what this is. The tau. Okay, it's 1 over 12,000. 12,500. Okay. So I'm going to move the 20 to the other side and move the VO to the other side. And I'm going to have 20 divided by tau is voltage. Okay. Wait, hold on. 20. I'll just leave it as this for now. So we'll say that 20 divided by tau is 25,000. Divide both sides by 80. Yeah. Just want to make sure our math worked out. Okay, so we're going to move the negative VO to the other side and move the 20 to the other side and divide everything by the time constant, which is 80 microseconds. So that's going to end up being dVOT dt plus VOT 1 over 12,500 equals 25 minus 25 or 250,000. Now we already know that if we multiply k times tau, we're going to get the VC infinity, but we already know it's going to be negative 20 volts. And the math will prove it. If you multiply this out, then you're going to get 20. So anyway, let's go ahead and write our solution for the voltage. Say that VOT equals minus 20 plus 20 e to the minus 12,500 t volts. And we'll say that is for the interval 0 t to less than 10 microseconds. Now, as I mentioned before, 10 microseconds right here is not a long time. And the time constant for the circuit is 80 microseconds. So it takes about 5 time constants for a circuit to reach the steady state. 5 time constants here would be 400 microseconds. Now, we don't have enough time for this capacitor to fully charge, so we can't say that whenever we flip the second switch that the initial voltage will be minus 20 volts, the final voltage for the circuit. So we're going to find out what VO at 10 microseconds is, which is the time, maybe the initial voltage just before the switch is thrown. My pen is acting up. Hopefully it fixes itself. Hold on. I'll be right back. It's not, I gotta close OneNote. Sorry about that. I think it should be working now. Test my pen. Okay, good. So now we want to find VO at 10 microseconds. Or, sorry, 10 microseconds. That's easy. All I gotta do is plug in chug. We're gonna have minus 20 plus 20 e to the minus 20 or 12,500 t, and t is 10 microseconds. So that's going to be 20 times e to the minus 2000 t. That is, okay, so VO at 10 microseconds is going to be 2.35 volts, or minus 2.35 volts. We're going to keep that in mind for when we cycle the second half of the circuit. And like I said, we don't have very much time, so it didn't charge up very much. So we didn't get close to what our final voltage would have been. So now we're going to consider the second case, which is we have this bit of circuitry connected to this part. This 16 kilo ohms resistor and everything. So I'll say for t greater than 10 microseconds to infinity. So basically, just that. Now this time I'm going to find the equivalent resistance first, because we have an extra resistor in here, and that just makes it a little teeny bit more complicated. Not actually complicated, but one more thing we have to worry about. So I'm going to take the capacitor out of this equation, so to speak, because we don't care about it, because it's not going to influence the internal resistance or the equivalent resistance. So yeah, we're going to short out the voltage source, open up the current source. This is 4K. This is 16K. Here's A, here's B. R equivalent is going to be 16K in parallel with 4K. So it ends up being 3.2K. Now we already have our initial condition VO0, or I shouldn't say 0 anymore, 10 microseconds minus equals VO 10 microseconds plus, which is minus 2.35 volts. Now we need to find the final. We can do that a number of ways, but I'm going to go ahead and we're basically going to solve the DC equivalent of the circuit. So I'm going to write it all out. Here's a current source, still 5 milliamps. Going to be in parallel with this resistor. It's 4 kilo ohms still. Capacitor, 20 nanofarad. And we have resistor, 16 kilo ohms. Let me try to make this a little bit smaller, actually. There's no reason for it to be this big. Come on. Okay. Let's pull this in some. So I usually pre-draw these because I make mistakes. Sorry, I gotta pause real quick. OneNote is acting up. Okay, sorry about a second interruption. I guess OneNote doesn't like it whenever you have multiple files open at the same time. That's fine. So basically what we're doing here is we're going to find out what the VC infinity is by analyzing the circuit at the steady state. Now infinity is just a math thing, because if you look at the mathematical models for the voltages are exponential decay, and they technically never reach 0 in the mathematical world, so they just say infinity. But in a real circuit, it takes about, like I said, 5 time constants for the capacitor to fully charge or discharge. Same is true of inductors. Anyway, so we're going to find out what the final voltage of the capacitor is by analyzing it at the DC steady state. Now, at the steady state, VC infinity is going to be a constant. There's not going to be a change in the voltage anymore. So the derivative of a constant is 0, which means that this is 0. This is 0. So we're basically going back to the first circuits we ever did, where it was just resistors and current sources. So we're going to have a, let's see, minus VO over 4. I'll leave it in K just so I can neglect the M. So minus 4, and then 30 minus VO over 16K equals 5 milliamps. Now I'm neglecting their orders of magnitude because they're going to cancel out. So we're going to multiply everything out. See, minus 4 VO plus 30 minus VO equals 16 times 5 is 60, no 80. 80. Okay, so that means that VO infinity is going to be 50 divided by negative 5, which is minus 10 volts. Okay. Now we already calculated REQ, calculated VO initial at 10 microseconds and VO infinity. So we're going to use that to find our final expression for the voltage. So VOT is going to be VO infinity. And then let's see, it's not 2, minus 2.35 minus 10 equals 7.65. I'm pretty sure that's right. Anyway, so that's going to become plus 7.65 e to the minus. Let's find what tau is real quickly. I forgot to do that. So tau is going to be R times C. And let's see. C is 20 nanofarad times 3200. That is 1 over 15625. So this is going to become 15625 T. And we're going to have to put brackets here because we're shifting in time our 0 point, basically. 10 microseconds. We make that a bracket. And that's volts. So this is going to be for T. Let me start this. There. So from 10 microseconds onward, that will be another model for the voltage across that capacitor. So don't be intimidated by the double switches. It's nothing different. We're just basically analyzing a circuit that has a different way to calculate the initial voltage. Okay, so 7.81 is not too different from the last problem. We're going to basically be analyzing two transients, and this rising and this falling edge of this constant current pulse. So the constant current pulse starts at 0 and lasts for 75 microseconds, as given by the graph, and we'll use that to determine the behavior of the circuit. So to find the initial current in the inductor, we just go back here. We see 0 minus is 0. And that can't change instantaneously in the inductor. So that means that the current through the inductor is 0. I should actually write IO instead of IL. And that means since there's no current in the circuit, then the voltage drop across the resistor is 0. So that means that the initial voltage is 0 just before the current pulse happens. But the current or the voltage across the inductor can change instantaneously, and we'll find that it does with this resistor. So we know that 25 milliamps is flowing through it, and it's a 2 kilo ohm resistor. Through Ohm's law, the voltage drop must be 50 volts. So 0 volts, 50 volts. And as we tend toward infinity, the inductor is going to act like a short circuit. So VO infinity will be 0 volts. And we're going to use all that information later to find out the behavior of the circuit. So first thing we got to do is use our math. Now I went ahead and prepared these KCL and EFCs. And just like the capacitor one, we can't drop this I of t straight in there. We have to find an expression for I of t. So we cross that. We can't do that. But luckily, we have an expression for I of t. It's just 25 milliamps plus I of t. So let's plug that in and get to work. So VOT is going to equal 1/4, which is a 250 millihenry. That's leaving it as a fraction for now. And the derivative with respect to time of 25 milliamps plus I of t, or an expression that is minus VOT divided by 2K dt. Now, constant derivative of the constant goes to 0. I'm going to pull this minus out front, pull this 2K out front, and move the negative side, or the minus. I'll add whatever this whole expression is, being negative, to both sides, and we'll have it the same in our standard form, almost. So I'm going to move 1/4, and then 1/2K, and dVOT dt plus VOT equals 0. This is actually R over R, so L over R is tau, incidentally. So let's see, 1/4 of 2K, it's going to be like 1/10,000, right? Let me think. No, that'd be 2,500, so it has to be 1/8,000. I don't need to do any math for that. Let's see. So that means dVOT dt is going to be VOT 1/8,000 for tau, and K is 0. Now we already determined that V infinity was 0, but we can prove it. K times tau is 0 volts. So now let's go ahead and get our final expression for the voltage, and we'll use that to find the current. So VOT is going to be V infinity, which is 0, plus V initial minus V infinity, which is, so 50 minus 0, that's 50 e to the minus 8,000 t volts. Now the question asks for, I believe, IOT, right? That's for both of them. Okay. We can get IOT using the equation we derived earlier. So it's I of t is going to be minus VOT, so minus 50 e to the minus 8,000 t divided by 2K. So I'm going to take this K, I'll just make it milliamps. So 50 divided by 2 is 25. So IOT is 25. Wait, hold on. Am I missing something? Oh, yes. I'm sorry. I knew it looked wrong. We have an expression for IOT is 25 milliamps minus, or sorry, plus minus VOT over 2K. Now we know VOT is going to be minus 50 e to the minus 8,000 t So we're going to have 25 minus 50 divided by 2 is 25. E to the minus 8,000 T milliamps. Okay. So that is the current and voltage for this whole thing. If this current pulse remained constant, that's how it would end up being, but it doesn't. So these two are defined for the interval 0 t less than 75 microseconds. So now we're going to consider it after. Now, I75 microseconds, or IO 75 microseconds, is going to have to be IO 75 microseconds plus, because the current in the inductor cannot change instantaneously, we take away that current, because the current is going to go to 0, right? We can't change instantaneously. The current in the resistor can, and that's going to change our voltage. But anyway, so we're going to plug in 25 minus 25 e to the minus 8,000 times 75 microseconds. That ends up being 11.28 milliamps. And I infinity, we know is going to be 0 because there's no more current source, no more, well, the current source is there, but it's not providing any current. It's shut off. So we can say that the time constant is not going to change. We know it's currently 1 over 8,000. So we can say that IOT is going to be the initial current, or sorry, the I infinity, which is 0, plus the initial current minus the infinity current. So 11.28 minus 0, e to the minus 8,000 T milliamps. Oh, actually, minor caveat. We have to shift in time. So T minus 75 microseconds. Otherwise, that will be the wrong answer. So let's see, milliamps. Okay. And this is for the interval from 75 microseconds onward to infinity. So using this information, we can find out what the question asks for VO 75, 0, just before the 75 and just after the 75. Okay, so we already know what one of them is, 11.28 milliamps. So we now just have to find out what VO 75, or immediately before 75 microseconds, and then VO immediately after 75 microseconds have passed. So to do that, we already know what it's going to be immediately before. If we plug in that if we want to find the initial one, we're going to do 50. Let me just go ahead and write this up. It's going to be 50 times e to the minus 8,000 times 75 microseconds, which is 27-ish, say 27.4 volts. So that's going to be immediately before and after 75 microseconds plus. This one we're going to have to go back to our equation for the component. Now, we had IO equals negative VOT over 2K. So if we have IOT, we can get VO if we just multiply by 2K and divide by -1. So negative IOT times 2K equals VOT. So we're going to plug it in the current at 75 microseconds plus, which we know is 11.28 milliamps. So 11.28, or negative 11.28 milliamps times 2 kilo ohms. So I'm just going to remove that. It's going to become negative 22.56 volts. So yeah, you can see that the voltage can change instantaneously. In fact, the inductor is trying to resist that change in the current, so it pushes a back EMF as the magnetic field is collapsing. And that's where you get that negative voltage. So you got to be careful with whenever you're using inductors in practical circuits. So that is all of the mutual inductance problems. I hope these have been helpful, and I'll see you guys for the next one.